Let's try a couple of examples involving exponential decay. We'll start with Valium metabolism. The drug Valium is eliminated from the bloodstream with a half-life of 36 hours. Suppose a patient receives an initial dose of 20 milligrams of Valium at midnight. How much Valium is in the patient's blood at noon the next day? When will the Valium concentration reach 10% of its initial level? Well, all of these growth and decay problems stem back to the same equation for exponential growth and decay. Y equals y naught e to the kt. And remember that y naught is the initial value, y is the new value, and k is the rate constant. Well, since we know what the half-life for this drug is, we can use the half-life equation to get k. So our approach will be to use the half-life equation to solve for k, and then plug that back into the exponential growth and decay equation. So let's see, it gives us 36 hours. That's going to be t sub 1 half. That's our half-life right there. So to solve for k, we have 36 equals natural log of 1 half all over k. So k must be natural log of 1 half over 36. All right, that will be useful. Now let's go ahead and use our equation for exponential growth and decay to find out how much Valium is left in the patient's blood at noon. Well, the drug was given at midnight, and we want to know what happens at noon. So T then is 12 hours. Okay, so that's another useful piece of information. Okay, so let's start plugging things in. The new amount, which is what we want, equals the original amount, 20 milligrams, that's our y naught, e to the k, well, we decided that k was natural log of 1 half all over 36, times time, which is 12. And if you're feeling fancy, you can even simplify here. The 12 and the 36 cancel, giving us a 3. So really what we have to compute is 20 e to the natural log 1 half all over 3, or just the natural log 1 half over 3. Plugging that into a calculator gives about 15.87, and then we're working in milligrams for our units. And that's a reasonable answer, right? They gave 20 milligrams at midnight, half-life is 36 hours. So after 12 hours, yeah, we'd expect about 15 milligrams or 16 milligrams to be left. Totally reasonable answer. Let's answer the next part of this. When will the Valium concentration reach 10% of its initial level? Well, again, we start with our equation for exponential growth and decay, y equals y naught e to the kt. We know what k is. Okay, t is what we're solving for. And when the current amount reaches 10% of the initial amount, we have the current amount y equals 10%, so that's 0.1 of the original amount, y naught. Okay, so we can plug that in here for y, and we get 0.1 y naught equals y naught e to the kt. And then look, these y naughts cancel out. So we essentially are working with 0.1 equals e to the kt. And now I'll sub in our value for k, natural log 1 half over 36 all times t. So now we just need to solve this for t. Remember, anytime the variable is stuck in the exponent, we use a natural log to get it down. So let's hit both sides with the natural log. That's going to take this whole cluster of stuff down to the front, and then the remaining natural log of e is simply 1. So we have natural log of 0.1 equals natural log of 1 half over 36 times t. Well, we can solve that for t. T is then 36 natural log of 0.1 all over natural log of 1 half. Put that into a calculator, you get about 119.59 hours. So that's quite a while. So we can see that Valium is a very long-acting drug. And these are things they need to consider in the medical community. In some situations, you might want to give a patient a very long-acting drug. In other situations, the patient may need a very short-acting drug. For instance, if they have a procedure the next day in which none of this or very little of this substance could be in their system, they would have to give a much shorter acting drug. So it's hugely important to know the half-lives of these drugs and how to work with them. Let's try an example involving radioactive decay and uranium. Okay, uranium dating. Uranium-238, also known as U-238, has a half-life of 4.5 billion years. Geologists find a rock containing a mixture of U-238 and lead, and they determine that 85% of the original U-238 remains. The other 15% has decayed into lead. How old is the rock? Alright, so scientists can use these radioactive dating methods to date various things. In this case, we're dating a rock, but you can also use the carbon decay to date various artifacts made by humans. It's a very, very useful technique. Let's see how it works. We have our same equation for exponential growth and decay. Y equals y naught e to the kt. Again, along with our equation for half-life. T sub 1/2 equals natural log of 1/2 over k. Well, we'll work all of this in terms of billions of years, so 4.5 will be our T sub 1/2. We proceed just like before in the Valium example to solve for k, except for this time the half-life is 4.5. This gives k equals natural log of 1/2 over 4.5. The question is asking how old is the rock, so what we'll be solving for here is t. So we'll take this k that we've solved for down here, plug it in for the k up here. Well, let's take a look at these y's and y naughts, all that here. We have 85% of the original 238 remains. So that tells us that the current amount is 0.85, 85% of the original amount, y naught. So we plug that in up here for y. So we're plugging in a lot of things into our equation for exponential decay. We have 0.85 y naught equals y naught e to the k, which is natural log of 1/2 over 4.5 times t. Again, the y naughts cancel out, and we're left with 0.85 equals e to the natural log 1/2 over 4.5 times t. Well, our variable is stuck in the exponent, so we natural log both sides to get it down, right? So then all of this comes down to the front, and we're left with natural log of 0.85 equals all this natural log of 1/2 over 4.5 times t. We can then solve that for t, so we have t equals about 4.5 times natural log of 0.85, all divided by natural log of 1/2. Into the calculator it all goes, and we get about 1.055. And remember, that's in billions of years, so this is billion years. Okay, so very, very old rock, and a profoundly useful technique for dating ancient items.